This question is about measuring the acceleration of free fall g. A student undertakes an experiment to measure the acceleration of free fall. Figure 1 shows a steel sphere attached by a string to a steel bar. The bar is hinged at the top and acts as a pendulum. When the string is burnt through with a match, the sphere falls vertically from rest and the bar swings clockwise. As the bar reaches the vertical position, the sphere hits it and makes a mark on a sheet of pressure-sensitive paper that is attached to the bar. So we've got a diagram here that shows that swinging of the bar, and it comes down to meet that sphere when it's fallen a certain distance. The student needs to measure the distance d fallen by the sphere in time t taken for the bar to reach the vertical position. To measure d, the student marks the initial position of the sphere on the paper. The student then measures the distance between the initial mark and the mark made by the sphere after falling. To measure t, the student sets the bar swinging without the string attached and determines the time for the bar to swing through 10 small angle oscillations. Figure 2 shows the strip of paper after it's been removed from the bar. The initial position of the sphere and the final mark are shown. Mark on Figure 2 the distance that the student should measure in order to determine d. And this is for 1 mark. Now what we need to think about for this question is which part of the sphere we want to measure the movement of. Now I would say that for this question it's going to be the movement of the centre of the sphere, because the point level with the centre of mass of the sphere is the bit that's going to be in contact with the paper. If you picture your sphere and your piece of paper, you can see that actually the centre of mass is level vertically with the contact points. So let's mark the distance from the centre of the sphere across to the contact point where the sphere first hits the paper. Remember, the sphere is moving from right to left. And there's your 1 mark. Now make sure that you're really clear on where those positions are. You might actually lose that mark if you mark anywhere other than the right hand side of that mark where the sphere hits the paper, because actually the sphere has already made contact with the paper if you're looking at this area over here. So do be really careful. The student repeats the procedure several times. Data for the experiment is shown in table 1. And then we've got that table there with a set of distances. Time for bar to swing through 10 oscillations as measured by a stop clock is equal to 15.7 seconds. Calculate the time for 1 oscillation and hence the time t for the bar to reach the vertical position. Now for this 1 mark question, you will only get a mark for getting the correct answer, but we'll write down the working anyway. Now, it says there the time for 10 oscillations is going to be 15.7 seconds. So let's work out the time for 1 oscillation first. So 1.57 seconds for 1 full oscillation. Now we're only interested in the time taken for the bar to move from its most extreme point down to the center, which is actually just a quarter of an oscillation. So we need to divide this time, 1.57 seconds, by 4, and that's actually the time taken for the bar to fall to the vertical position. So we end up with 0.3925 seconds. I'm going to round that to 0.393 seconds so that it's to 3 significant figures, the same as the value that's given to us in the question. Determine the percentage uncertainty in the time t suggested by the precision of the recorded data. Now, we were given a time of 15.7 seconds, which means that that's timer is correct to the nearest 0.1 seconds. So the uncertainty in this value is going to be 0.1 seconds. Now we need to divide this value by the overall value itself to get the percentage uncertainty. So we have 0.64% uncertainty, and that will actually be the same as the percentage uncertainty in the time taken for the bar to fall, because the percentage uncertainty in a quarter oscillation is the same as the percentage uncertainty in a full oscillation. The absolute uncertainties are different, but the percentage uncertainty scale up, so we use the same value here. It's worth just including a note that that is the percentage uncertainty in the time taken to fall. For this question, you get 1 mark for correctly identifying that it's 0.64%, and then a second mark for saying that it's the same percentage uncertainty as that's for the time taken for a quarter oscillation or for the bar to fall. Use the data from table 1 to calculate a value for D. So if we go back to table 1, we're given 6 values here. Before we calculate a value for a mean, we need to check for any anomalies. I would say that the 4th value here is an anomaly, 0.701. It doesn't really line up with the rest of the values. It's quite far away. So let's calculate a mean for the other values. So we end up with 0.759 meters. Let's just summarize that down in this part of the question. So we end up with 0.759 meters. You may want to do your calculations in this part of the question rather than next to the table, just so the examiner knows how you've done your working. For this question, you get 1 mark for correctly identifying the anomaly, so 0.701 meters, and then another mark for correctly calculating the mean using the other values. Calculate the absolute uncertainty in your value of D. Now for this part, we need to find the range of those values. We need to find the difference between the largest value and the smallest value, and that should be 0.026 meters. Now, it might just be worth doing that as a calculation. So let's just look back at the table just to see why that is. We can see here that the largest value is 0.772 and the smallest value is 0.746. So let's just write that down here. So the absolute uncertainty is going to be the distance from the center point between those two values and the most extreme. So it's going to be half of that value. So 1 mark for that one. Determine a value for G and the absolute uncertainty in G. So the first thing we want to do is calculate the value for G itself. For this one, I would use the equation S equals UT plus half AT squared. So from this, displacement is S, initial velocity is U, time is T, and acceleration is A. However, this will be equal to a half AT squared because U is equal to 0 because it's at free fall, so it's starting at 0 meters per second. Now, if we rearrange this equation, we can actually say that A is equal to 2S divided by T squared. And A is going to be the value of G that we're looking for, so we just need to substitute the values into that equation, which gives us 9.83 meters per second squared. So that's our value to begin with, and that will be our first mark of the 3. To calculate the percentage uncertainty, we first need to find the percentage uncertainty in the distance so that we can combine it with the percentage uncertainty in the time. So percentage uncertainty in distance, we need to divide the absolute uncertainty by the value itself. So we've got 1.7% for the percentage uncertainty in distance. You get another mark for correctly calculating that. Now we need to combine that with the percentage uncertainty in the time. Now bear in mind that where we're squaring the time in this initial calculation, we're going to need to double the percentage uncertainty in the time. Now, that follows the rule that when you are raising a value to a power, its percentage uncertainty needs to be doubled. So we're going to add the 1.7% to that double 0.64% because we're dividing that displacement by the time squared. So the calculation should look like this. And that should give us 3.0%. So to find the absolute uncertainty in that value, what we need to do is multiply that percentage uncertainty by the value itself. So we need to do 3% of 9.83 meters per second squared. And that gives us a value of 0.3 meters per second squared. Now, the uncertainty must have the same number of decimal places as the actual value itself. So the way that we would truly write this is as follows. but writing it as 9.83 is fine. So just to summarize that final mark there, you would get the third mark for correctly calculating that uncertainty to be 0.30 meters per second squared. Discuss one change that could be made to reduce the uncertainty in the experiment. Now, there are a range of things that you could write for this question. I'm going to give some examples, and then we'll go through and discuss them. Now remember, you don't need to write this much for the 2-mark question. You're going to get 1 mark for a given change, a sensible change, and a reason. So the first thing we could do is use a pointed mass instead of a full sphere. So the reason for that is that the uncertainty is most affected by the measurement of d. Remember that we calculated the percentage uncertainty in the distance to be 1.7% compared to the time, which was only 0.64%. But more specifically, you'll get a finer point, a more defined mark on that bar. Another example. So if we use a larger number of swings, what you'll find is that actually the percentage uncertainty will be reduced because the absolute uncertainty in the time calculation remains the same, but it's a smaller proportion of a larger time. So the last example that I'm going to give is to use a longer or a heavier bar. And the reason why that's important is because as that bar swings down, if it takes longer, then that time recording is going to be much larger. And what that then means is that where the absolute uncertainty in the time measurement remains the same, it will then also be a smaller proportion of that overall value itself. So it's a similar reasoning to the second point, actually, with the larger number of swings. We just want that overall time measurement to be as long as possible so that the absolute uncertainty is a smaller proportion of the overall value. The student modifies the experiment by progressively shortening the bar so that the time for an oscillation becomes shorter. The student collects data of distance fallen s and corresponding times t over a range of times. Suggest giving a clear explanation how these data should be analysed to obtain a value for g. Now, there are 3 marks up for grabs here, so let's think about how we can obtain those. We know first of all that there's a relationship between the displacement or the distance fallen and the time taken. We wrote that down before, let's just write it again. Now, it should be noted here that the full equation is s equals ut plus half at squared, but remember the value of u is 0 because it's falling from rest. So we could plot a graph of s against t squared to find that value of a. Remember that a is the acceleration, which would be the value of g. Now, using that graph, we want to find the gradient, like I just said. If we put s on the y-axis and t squared on the x-axis, the gradient of that graph should be half a. So then your 3 marks for that question are the 3 latter points, not the equation at the top. Any of those points missed and you would lose a mark, although it would be unusual to miss the 2nd mark but get the 3rd mark because you're talking about a gradient of a graph. So it's likely that you'll either get 1 mark or 3 marks in this question, but be as clear and as specific as you can. This question is about capacitor charging and discharging. A student designs an experiment to charge a capacitor using a constant current. Figure 3 shows the circuit the student designed to allow charge to flow onto a capacitor that has been initially discharged. And here's our diagram, fairly straightforward. You can see there's a variable resistor there connected to a capacitor, voltmeter and ammeter, and then you've got a switch and a cell. There's also a shorting lead there that goes across the capacitor. The student begins the experiment with a shorting lead connected across the capacitor as in figure 3. The variable resistor is then adjusted to give a suitable ammeter reading. The shorting lead is removed so the capacitor begins to charge. At the same instant, the stop clock is started. The student intends to measure the potential difference, the PD, across the capacitor at 10-second intervals while adjusting the variable resistor to keep the charging current constant. The power supply has an EMF of 6 volts and negligible internal resistance. The capacitor has a capacitance of 680 microfarads. The variable resistor has a maximum resistance of 100 kilo ohms. The student chooses a digital voltmeter for the experiment. A digital voltmeter has a very high resistance. Explain why it is important to use a voltmeter with a very high resistance. Now, if we look back at our diagram, we can see why that resistance is important. So if we think of this parallel system with the voltmeter and the capacitor, we're interested in having the current flow one way and not the other. Now, if the voltmeter has got a very high resistance, then that means there's going to be a low current flowing through it. And that's according to Ohm's law. Now, of course, this is the equation form of Ohm's law. It tells us that V equals IR. So basically, the current is inversely proportional to resistance. So what that then means is that if there's less current going through this branch, then there's going to be more current going through this branch, or a higher proportion of that current. So less charge is going to be lost through that voltmeter. So if we go back to our answer space, so if there's a higher resistance, the current through that voltmeter will be lower, so we will lose less charge through that voltmeter. Suggest one advantage of using an analog ammeter rather than a digital ammeter for this experiment. Now, when you think about a digital ammeter, you've got a reading which is going to be to a certain number of significant figures, and that value, the true value, is going to jump between those two very discrete points. However, if you're looking at an analog ammeter, it's more of a continuous scale, and you can look at the positions between the markings. What you'll also find is that if you need to find the difference between two values on that ammeter scale, then you can mark them off. You can put a piece of paper over the ammeter scale, and you don't need to worry about recording down individual values of currents. So I would say the point to make here is that you can make markings on the scale, which can then be read off later. Suggest a suitable full-scale deflection for an analog ammeter to be used in the experiments. So in order to calculate this value, we need to first of all work out what the current is going to be to start with, because that's when it's going to be at its highest. So the way to find the current is going to be by dividing the voltage by the resistance. So remember, we're starting with 6 volts, and we're going to divide by 100,000 ohms. And that should give us 6 times 10 to the minus 5 amps, which is approximately 60 microamps. And there's your first mark. So for this full-scale deflection, what we need to do is use a value that's above the value that we've calculated, but not too high. Otherwise, the reading that we're going to get is going to be too low. So it's recommended that you use something like 100 microamps or 200 microamps, but if you're going to use something like 250, then that's not going to be appropriate. It's going to be too high. So either 100 or 200. It's a bit like choosing fuses for an electrical appliance. They're set at certain values. So let's go with 100 microamps. And then that's your second mark. The diagram shows the reading on the voltmeter at one instant during the experiment. The manufacturer gives the uncertainty in the meter reading as 2%. Calculate the absolute uncertainty in this reading. So to calculate this, we just need to multiply the percentage uncertainty by the value itself, and that will give us the absolute uncertainty. So we want to find 2% of 2.39 volts. But I'm going to round that to 0.05 volts to keep it to one significant figure, as it's an uncertainty. Determine the number of different readings the student will be able to take before the capacitor becomes fully charged. And to work this question out, we've got the charge that the capacitor can store, and we work that out using the capacitance. We'll do that in a second. And we're given a current as well, which is just the current that we calculated before. And what we can do is use that to calculate a time. Now, bear in mind that there's going to be a reading taken every 10 seconds. So what we can do is divide that total charge time by the time taken for one recording, and that will give us the number of recordings. So the first mark is just to use Q equals CV to find the charge. So So we've got 4.08 times 10 to the minus 3 coulombs, or 4.08 millicoulombs. Now let's use the equation charge equals current times time, and therefore time is equal to charge divided by current. That will give us 68 seconds. Now we're looking at the number of whole time periods there in which readings can be taken. So we can't quite take 7 readings because we haven't got a full 70 seconds. So only 6 readings can be taken. So in terms of where these marks can be allocated, we get 1 mark for correctly calculating the charge, another mark for correctly calculating the amount of time, and then a third and final mark for correctly identifying that it would be 6 readings and not 7. The experiment is performed with a capacitor of nominal value 680 microfarads and a manufacturing tolerance of plus or minus 5%. In this experiment, the charging current is maintained at 65 microamps. The data from the experiment produces a straight line graph for the variation of PD with time. This shows that the PD across the capacitor increases at a rate of 98 millivolts per second. Calculate the capacitance of the capacitor. So the first thing to note is that actually this 65 microamps is going to be 65 microcoulombs per second. Remember, an amp is a coulomb of charge per second. So let's write that down first of all. We've also got 98 millivolts per second. So to calculate the capacitance, let's use Q equals CV and say that C is equal to Q divided by V. Now what we can establish here is a given time for these things to occur. So instead of using number of volts or number of coulombs, let's use volts per second and coulombs per second and incorporate that time period into there. So actually this calculation remains the same because we've got a T on the top and a T on the bottom. So these are the actual values that we've got. We've got Q divided by T, or charge per second, which is 65 microcoulombs per second. And we've also got 98 millivolts per second, or the voltage per unit time. So let's put those in. And that should give us a value of 6.6 times 10 to the minus 4 farads, or 660 microfarads. Now, in terms of where those marks are obtained, we get the first mark for correctly identifying that we can use Q divided by T and V divided by T, and actually putting that calculation together. And then a mark for getting the correct answer at the end. Deduce whether the capacitor is within the manufacturer's tolerance. Now, we've obtained a value of 660 microfarads, and what we need to work out is whether that falls within that tolerance range of 680 plus or minus 5%. So 5% of 680 is going to be 34 microfarads. So actually, that value can be anywhere between 646 and 714. Because 660 is within that value, then it is within the manufacturer's tolerance. The student decides to confirm the value of the capacitance by first determining the time constant of the circuit when the capacitor discharges through a fixed resistor. Describe an experiment to do this. Include in your answer a circuit diagram, an outline of a procedure, and an explanation of how you would use the data to determine the time constant. Now, the first mark for this question, you can see there are 4 marks there, will be for correctly drawing the diagram. So I'm going to draw a diagram and then we'll talk through exactly why it is the way it is. So we've got here our capacitor charging circuit initially. You can see that I've connected the switch across the top, which means that current is going to flow through the battery, which is on the left-hand side. Notice the lines are different sizes. It's going to pass through the capacitor, the lines are the same size here, and then through the resistor. So we're actually charging the capacitor through the resistor. As soon as we change the points on the switch, we can actually remove the battery or the cell, and we can discharge this capacitor through this resistor. You'll notice if I connect this point, the two points on the right hand side, the battery is completely removed. Now we've also got an ammeter there to measure the current at all times, and a voltmeter here to measure the potential difference across the capacitor, because those are the readings that we need to take for our data later on. So next we're going to have a look at our method, what we're actually going to do with this circuit, and then how we're going to analyze our data to obtain results. So your first mark for this diagram. Charge the capacitor fully and then discharge it through the resistor at intervals of 10 seconds. Now this is going to give us quite a nice exponential graph, which we're going to want to plot. So we can either use potential difference versus time, or we can use current versus time. Both of them are going to decrease exponentially, and both of them are going to have a gradient of 1 over the product of the resistance of the resistor and the capacitance of the capacitor. And like I said, instead of V, you can just put I. It's up to you. And then the gradient of the graph is going to be 1 divided by the resistance multiplied by the capacitance. So those are your 3 marks there. Now there are variations that we can make on this. The discharge part with the intervals of 10 seconds, that remains the same. But what you could do is, instead of finding the gradient of the graph, you could find the time taken for the value of voltage or current to reduce to 1 over E of its original value. And that would help you to find the time constant as well. In theory, you could do this without plotting a graph as well. You could just look at the data itself and work out the time taken to drop to half. It's that kind of half-life calculation if you wanted to do that as well. Remember, there's a factor of natural log of 2 to consider there. So what we'll do is we'll write down some alternate ideas here. So there's that natural log of 2, and if you divide that by the half-life, you'll end up with 1 over RC, or 1 over the time constant of that capacitor resistor system. Then, like I said, what you can also do is find the time that it takes to fall to technically 37% of its initial value, which is 1 over E of its original value. And then those are your 2 other methods of analysis there. Figure 4 shows how the refractive index N of a type of glass varies with the wavelength of light passing through the glass. The data for plotting the graph were determined by experiment. And then in figure 4 here, we've got a big graph with refractive indices on the y-axis and wavelengths on the x-axis. A student says that figure 4 resembles that of the decay of radioactive atomic nuclei with time, and that it shows half-life behavior. Comment on whether the student is correct. Well, in reality, we know that by combining a few equations together, this isn't going to be a half-life style graph. There's no part of this region of physics that is in any way exponential. Should we just jot those down anyway? So you can see there that actually the refractive index is inversely proportional to wavelength, which is why it has that shape of graph. That's not enough for this question though, because we're determining this experimentally. So the assumption is that we don't know those equations, that we don't have access to them. So let's look back at the graph. Now, what you could say from this is that actually it does appear to half every regular interval as it would do on a radioactive graph. So if we just mark that off, so as you can see there, within the first 100 nanometer interval, we drop by 4 units, and in the second, from 400 to 500, we drop by 2 units, and in the third, we drop by 1 unit. And by units, I mean 5 small squares. And that behaves in a very similar way to a radioactive half-life graph, because it appears to be halving each time over a regular interval. Now, we could write that in that question box, and that would be correct. So that's your argument for saying the student is correct. You could also argue that the student is not correct. For example, that's not the origin what appears to be the origin of this graph is actually at 300, 1.6020. So this shape of graph isn't centering around 0, 0. So it's not a true radioactive half-life shape of graph, if you like. You could also say that the value of n isn't halving every interval like it would in a real radioactive graph. It appears to halve, and with the x and y axis values that we've chosen, it looks like it's halving each time as I've drawn, but actually that's not a true halving, because it's if you extrapolate this graph all the way down to 0, it's actually dropping by a comparatively small amount. But this works just as well, that it resembles that decay because it's dropping by 20 and then 10 and then 5 every regular interval, which is similar to what a radioactive half-life graph would do. The dispersion of glass is defined as the rate of change of its refractive index with wavelength. At a particular wavelength, d is equal to delta n divided by delta lambda. Determine d at a wavelength of 400 nanometers. State an appropriate unit for your answer. Now you'll notice here that delta n divided by delta lambda is the same as delta y divided by delta x, which is going to be the gradient of that graph. Remember, the n values are y values and the lambda values are x values. So we're just finding the gradient of this graph at the point where the wavelength is 400 nanometers. So we do need to draw a tangent so that we can work out that gradient appropriately. So let's look back at the graph. You can see I've circled here at 400 nanometers where we want to draw that tangent. So I'm going to draw the tangent now. And you'll see that that tangent passes straight through the points. Now, let's turn that into a triangle so that we can find the change in n and the change in lambda. So let's write those values of delta n and delta lambda down. So there are our values of delta n and delta lambda. Let's write those down in the answer space so that the examiner knows how we're doing our working. Let's write that 145 nanometers in meters. Now, to find that gradient, we need to divide delta n by delta lambda. So that gives us a value of 1.38 times 10 to the 4. Now, notice how the refractive index doesn't have a unit, but the wavelength does. So we'll end up with a value that has the units of meters to the minus 1. Now, typically, the answer that you can give is within a range. So anywhere between 1.3 and 1.7 times 10 to the 4 meters to the minus 1 should be fine. So you'll get 1 mark for correctly drawing your tangent and drawing a triangle. Another mark for using the correct values and making the calculation. And then the third mark is for getting the correct value or a value within that range, complete with a unit. So 3 marks. It is suggested that the relationship between n and lambda is of the form n equals a plus b divided by lambda squared, where a and b are constants. The data plotted in figure 4 are given in table 2. Now we've got a table here with 3 blank columns. We might not need to use all of those, as the question says later on, but it's going to come in handy very shortly, and we've got values of lambda and values of n. You are to determine a using a graph of n against 1 divided by lambda squared. Make any calculations that you need to in order to plot your graph. The columns in table 2 are for you to use to calculate and tabulate the derived data that you need. You may not need all the columns. So if we're going to plot a graph of n against 1 divided by lambda squared, it's going to be worth calculating those values of 1 divided by lambda squared. And it's probably worth converting those wavelengths into meters first. So let's use the first column to calculate our values in meters. And then once we've got those values of lambda, we can work out the values of 1 divided by lambda squared. Now you'll notice that I've put times 10 to the minus 12 in all of those cells in that table. You could, in theory, just put times 10 to the minus 12 meters to the minus 2 in the heading, and that might save you a little bit of time, and just put the front coefficients of the standard form in the table. but it's just a time-saving measure. So for this question, you'll get 1 mark for getting the correct column headings, another mark for getting all of your calculations correct, and then a 3rd mark for getting the correct number of significant figures. So put it to 3 significant figures as I've done here. Plot your graph on figure 5. The values of n are provided on the y-axis. So this should be fairly straightforward. As long as you've got the correct values of 1 over lambda squared, then you can put those straight onto the graph. Obviously, if you've got some of those answers wrong, then it's unlikely those errors will be carried forward. As long as the examiner can see that you've used the exact values that you're given in the table, then that should be fine. So let's first of all put a suitable scale on the x-axis. So you can see that the values of 1 over lambda squared range between 2.78 and 11.1. So what I'm going to do is I'm going to vary that from 0 up to 12. Now let's make sure that our axis labels are correct. You'll notice that the value of n is already on the y-axis. So using our table, let's put the correct points on the graph. So there are points plotted correctly on the graph. The next thing that we need to do is plot a line of best fit through those points. Just making sure that that line of best fit goes right the way down to the y-axis, because that's going to come in useful in a minute. And then your 3 marks are going to be firstly for correctly labeling the axes, correctly plotting the points which by eye can be seen as correct to within half a square, and then finally for correctly drawing the line of best fit. So those are your 3 marks. Use your graph to determine A. So if we write down that equation that was given to us at the beginning, what we can see is if this graph takes a y equals mx plus c format, so rearranging it slightly, we can actually write down y equals mx plus c underneath and see what the equivalents are for each symbol. So you can see where n takes the y values, where 1 over lambda squared takes the x values. The gradient of that graph in theory should be the value of b, but the value of a should be the y-intercept. So let's look back at our graph. That is somewhere between 1.6014 and 1.60145. So it needs to be corrected within half a square. It's quite precise, but if you've got the correct points and you've drawn the line of best fit correctly, then you'll get that mark. If you are slightly out, it is only a mark that you've lost, so it's not the worst thing. State the significance of A. Well, let's look at what A actually means here. If we're looking at A on its own, let's write it as A plus 0, first of all. Now that seems obvious, but actually, if we treat n as being equal to a plus b over lambda squared, we can write that underneath. So what we're saying there is a is the refractive index when b over lambda squared is equal to 0. Now, because we've got an inverse squared function here, if the value of b over lambda squared is going to be 0, then that means that the value of lambda squared is going to be very large, basically infinite. Now, because it's only asking you to state the significance of A, that's all you're going to get the mark for. So even with all of these calculations, the only bit that you're going to get the mark for is this last bit here. Another suggestion for the relationship between n and lambda is that n is equal to c times lambda to the power of d, where c and d are constants. Explain how d can be determined graphically. Do not attempt to carry out this analysis. So for this, we're going to have to use logarithms so that we can bring that power of d down from being a power so that it can be a gradient of a graph. And that gradient itself needs to be found from a straight line graph, which is going to have the equation y equals mx plus c. So the first thing we need to do is to take logs of both sides of that initial equation. And this is where your logarithm laws are going to come in. We're going to need to expand this out, and that's going to gain us our first mark. So the first thing to say is that when two values are multiplied within the brackets of a log, we can separate them out so that we're actually adding the logs together. The second thing to say is that when there's a power of a value inside a log, we can bring it out so that it's a multiple of the log itself, as you can see here. Now that we've got d as a multiple, we can actually put this into a straight line format. So writing that straight line equation underneath again, if we were to plot values of log n on the y-axis and values of log lambda on the x-axis, the gradient of the graph that we end up with is going to be d. As you can see there, m, the gradient, is correspondent to d. So here's what you need to write down. Plot a graph of log n on the y-axis against log lambda on the x-axis. When something's plotted against something else, that automatically means y against x anyway, so you don't really need to mention the y and x-axis. The gradient of this graph is equal to d, as can be seen from the straight line graph equation, represented by that value m. So for this question, the first mark will be obtained for correctly identifying the structure of the equation to put into the graph. The second mark will be for saying that you're plotting a graph of log n against log lambda. And then the third mark will be given for saying that the gradient of this graph is equal to d. So those are your 3 marks.